So this is a talk about inference in language and its relation to logic. Um, so the topic here is actually inference. So I could spend a whole hour at least on talking about what inference is, especially now that I work on it so much. But let me kind of give a kind of quick cut about this. So here's what I take inference to mean. So I'll say that a sentence follows from a list of other sentences if whenever a person accepted the list of assumptions, this capital gamma, they should or they could, in principle, accept phi. So it's a human acceptance of one sentence given a bunch of others. And here's what I'd like to think about. So here's a kind of very strong formulation of what this means for logicians. So I don't actually see this written out anywhere, but I take this as to mean what inference is in some sense. So in seeing whether phi actually follows from gamma in some situation, some context, some background, what we would do is we would put down a set of categorical sentences. I mean, sentences that are just background knowledge about the world and about the situation that we're in, that you use that are believed to be true in some sense. And they would be put down in some formal language. And everything about the background situation should be describable in that language. And then we would simply run, a general purpose theorem prover to see whether the sentence that we're interested in follows or it doesn't from the sentence. And I take it that even since like Leibniz, that we believe that such a thing should exist in principle. Such a procedure should exist to tell us whether something follows from something else. And the inference should actually be sound and complete, hopefully complete with respect to some semantics. And if it turns out that a person really didn't make the inference that logic says, then there should be some account of the discrepancy. And it should be an interesting story all around. Now, in some sense, I mean, I'm very interested in doing this and then actually seeing it, but at the same time, it's definitely a pipe dream. So it's never really been done in any kind of complete sense, or even in a partial sense. And I want to start this talk by saying why that really is. I think it's because in order to make progress on this problem of inference, you have to give up something. So logic, which is actually I guess the thing that I was trained in the most, actually gives up on language. It gives up on real language completely. So in logic, we study artificial languages that have very little to do with natural language, or the relation between natural language and logic is a fraught relationship. So that's what logic gives up. Now, you might think that all this should be done in linguistic semantics. And in fact, if you open up page 1 of a semantics textbook, it frequently will say, our job is to account for inference, when a human being would say that one sentence follows from another. But this page 1 is page 1. It is just to get the study off the ground, and nobody ever goes back to it. So I will show you something about inference today that could have been in any linguistics semantics textbook, but never was, for reasons that the real reason is because actually in linguistic semantics, we're not really interested in inference. We're interested in truth conditions and things like that. So this point about inference is lost there. Good old-fashioned AI, the next one, actually gives up on trying to do anything in a decidable system. So it formulates things in first-order logic. Well, I have a kind of prejudice against undecidable logical systems for this particular project. And also good old-fashioned AI gives up on any human competence too. But it does have something to say about inference. Psychology spends a lot of time talking about what human beings do and don't do in syllogistic inference, but it doesn't go beyond that. So all of the stuff that I'm going to be interested in today goes way beyond what psychologists have ever really thought about. And in the field that I'm mostly aiming at in this talk is what's called natural language inference, or NLI. It's a kind of sub-discipline of natural language processing, or even artificial intelligence sometimes. This one gives up on logic. This one gives up on logic and gives up on explainability. So I'll show you how all this one goes on. So what I'm trying to do is really the field of inference, merging it with logic and actually merging it with all of these things, but to put inference as the center of the action. Okay, so the program of natural logic that this talk is in a way part of is the idea is I would like to show that what people mean by inference, interesting parts can be done without translating natural language into anything else, or with a minimum of translation. And all the logical systems should be decidable. And in fact, they should be pretty light. What I mean by that is they should be low complexity, and the complexity of the whole thing, when you put them all together, might turn out to be undecidable. But each little piece of the inferential story should be a very small piece, as we would learn from something like cognitive science or computer science. I am trying to make connections with all kinds of fields of logic. And in some sense, I would like to rework the enterprise of semantics based on computational linguistics. Now, that's part of the backdrop. The other part of the backdrop is that since for the past 3 years or so, machine learning has done better than logic on anything like the task that I'm talking about. And so for the first time, computers do better than people. Intelligence, namely this inference. So I feel like as logicians, we are playing catch up, and so part of what I'm doing here is to describe the kind of response from the world of logic to the world of machine learning. So I wanted to start by showing you a little bit about how that stuff works. Let me just show you a touch of this. Can you all see this now? Yeah. Okay. So these are this is some of my projects on this subject. So in column B, I have a sentence, and in column C, I have a sentence. And I want to know whether it's an entailment, if C follows from B, or is neutral, which is this N, or is the contradiction C. So the first one says, the brown dog is running in the snow. Now, if I asked you that, would you agree a dog is running through the snow? So you have to read it very closely, and I think reading it closely the way we are trained to do sometimes in philosophy, in a way gets in the way. So if I say this one is running in the snow and this is running through the snow, I mean, is it really different? Does it really literally follow? Probably none of them actually follow to the letter, but most human beings would say entailment, and so I would like the computer system to actually say entailment. So we go through like 5,000 of these. We're going through thousands and thousands of these. This is I'm part of a group of people that gets together every week and talks about these. The yellow ones are ones that I thought I should discuss with my, my colleagues doing this. So this one here, a group of children is not playing tambourines. A group of children in a church basement is playing maracas and tambourines. So you think about it, okay, so I thought it was a contradiction, but I actually felt that maybe it's worth discussing. So this is the kind of thing that I would like to do, and this is what I would like a computer to do, and I would like to write the programs, and I would like to see it in action. And this is more than you can get from the linguistic tradition, which actually never really comes to anything like this. It might come to one or two of these, but in terms of getting something that actually gets a good part of this right, this is what I'm trying to do. So this is what a computer can do better than you can do in some sense. So what do I mean by that is, well, a lot of these are contradictory, but if we put up some that were clear entailments to a logician that a regular person on the street couldn't get, frequently a computer could get, because they kind of know the patterns behind the inference better than the accounts of inference that we bring to this task. Okay, so that's the kind of backdrop to all this stuff. Does anybody want to say anything to all this? I mean, I know this might be an unusual thing to do. Okay, nobody? Okay, I hope I haven't lost you. Okay. Okay. The directions that I'm going to try to do today. So there's a famous thing called the 80-20 rule, which comes from the economist Pareto, that 80% of the 80% of the gain in some task comes from 20% of the work, and the rest of the 80% of the work goes into the last 20%. So I think that for the 80% for the theory of human inference is monotonicity. That's what I want to show you a lot about today. So I would like to show you what I take to be the 80%, the bulk of the human being's inference, or at least something that does the work, the workhorse of inference for the human being, which I would take to be monotonicity. And the 20% I'm going to show will be natural logic rules that I'll try to show afterwards. And in all cases, if you do like we do in logic, actually even like we do in linguistics, to have a strict syntax. So that means the whole thing comes with a rigorous syntax, gets in the way of everything. So you have to have a syntax if you're going to do like logical rules. But at the same time, if you're going to appeal to like sentences as they come, like supposedly those sentences that I showed you, the rules can't be done in a strict syntax, or else they're not going to apply enough. So that's kind of my hobby horse for this. Okay, so I thought I would show you my video to start with. So this is about monotonicity. So let me give an introduction to this. So the National Science Foundation had a competition for called We Are Mathematics, and it was for 3 minutes videos on any subject and it should be ones that were non-technical. So it should turn people on to some kind of mathematics without any symbols. That's how I interpreted the rules. So I got challenged, and I made a video here, which didn't win. So I didn't win the competition, but I was a honorable mention. And I had never made a video before, so I try to show this off whenever I can. So here we go.
How can you answer a question involving words that you don't know? How can a computer do it? We'll see how, and we'll see how math enters in. Here's a sentence with some made-up words.
All the gloggle fish swifferate past a yub.
And now let's ask.
Do all striped begloggle fish swim past a yub?
To answer, let's take an ocean voyage to meet a begloggle fish. Some begloggle fish are striped. We put all this information in a scale. Up means more general, and down means more specific. They swim, and they swifferate. Here is the scale of the verbs move, swim, and swifferate. Supposing I tell you about a picture that
all the gloggle fish swim.
What would you be committed to? Here are the sentences that you would accept. These are what you infer from my statement. The pattern is, on the left, we move down the scale. On the right, we move up. When we change the word
all
to
some,
the pattern changes. And when we use the word
no,
the inference is different yet again. It's down both times. And when we start to look at other sentences and other words, we see the same kind of patterns all over the place. The same happens with numbers. Let's look for a second at 41 minus 32. The arrows tell us that to make 41 minus 32 bigger, we can either move 41 up or 32 down. Let's put numbers and language together. In mathematics, we put things which are similar under the same conceptual roof in order to study them together. That roof is called a preorder. It's what we are calling a scale. We think of a sentence like, all begloggle fish swim, to be the all function applied to a noun and a verb input. The language of preorders allows us to talk about increasing and decreasing functions. Let's go back and answer the question that we posed at the beginning. What you do and what a computer could do can be studied as an application of mathematics to everyday language.
Okay. Anybody want to ask about this? So what I'm going to do actually for the next 15 minutes or so is pretty much going to unpack this this video. Thanks. Thank you. Okay, so I'm going to, in a sense, unpack the math that's behind the video, and to show you how it's extended and implemented and stuff like that. Okay, so a lot of the work here is comes from papers of Johann von Bentham in the 1980s. So von Bentham basically saw that you could compute the arrows. So he basically, he didn't do this, but he saw that it could be done, that you could take a categorial grammar derivation tree and with a little bit of extra information, put in the arrows. So I'm sort of building on that. And although in fact, what I'm going to do opposes some of what, it goes in different directions. It definitely builds on his insight and his inspiration to do this. So he saw that you could do something like this. You could have a computer input sentences like these: every man and some woman sleeps, every man and no woman sleeps, a special report found no incriminating evidence. And these are actual examples from our system. And then you type these in, and then a few seconds later it comes out with the correct arrows. So every man and no, so man is down and some is up and woman is up and sleep is up. And there's this thing here, I'll have to explain this, equals in a minute. So basically, but Betham had the insight that you should be able to do something like this, input a sentence and have it tag the arrows afterwards. Now, let me show you why you would want to do that. So supposing you have these 5 sentences here: some dog hit some cat, some dog kissed no cat, most dog hit no cat, no dog hit no cat, with the arrows that are listed like that. And supposing you have a knowledge base back here, this is something that you learned from your parents or something like that, or you learned it from WordNet. You learned that dogs are animals. These are very typically taxonomic kinds of information. Poodles are dogs, birds. Okay, so the bird, I put this as a joke here because there's a name of a scooter called a bird, so I put that there. There's things about how modifiers, so typically modifiers go down. So hit vigorously is less than hit, things like that. You get the numbers, you get actually ones on numbers, the usual numbers, and you even get ones on the quantifiers, the determiners, like every implies most implies some, something like that. And now, so if somebody gives you these sentences 1 through 5 with the arrows, you get a kind of quickie theory of inference, because basically what it says is you could replace, like if you go up, so this dog, you go up, you could go up to animal and replace this one, and you could get some animal touch some animal. So hit, you can go up to touch according to this. Now, of course, these might be wrong. They might be temporary assumptions. It doesn't really matter. It's that this whole thing has an architecture that I'm doing the inference without translating it to first order logic. And in fact, I can't really translate it to first order logic because I have this most here, and the whole thing is higher order in a very serious way anyways. So we have most dog hit no cat. The most goes up, but I'm not going to replace it. I could replace it by some if I want. The dogs has an equals, and I'll show you about equals in a minute. Equals means I shouldn't replace it. Hit goes down to thrash as you go down here. No and cat, let's say no, I say all but at most one. This is a complicated story, but I claim that no should be less than all but at most one. And all Siameses are cats. So I claim that if somebody says most dogs hit no cat, and they're talking about some scene that they're looking at or something, it follows that most dogs thrashed all but at most one Siamese. So I claim these are inferences. And when I said before that this is my 80-20, is that this is my quickie theory of inference, is that actually if you have a computer system that can tag with these arrows, then, and you have a database of knowledge like this, then you basically can replace things and get a certain amount of the human inferences. This is what's going on in a certain amount of human level inference. Now, let me explain this. Now I'm sort of moving to the more mathish part of the whole thing. So I was told that some of you are math students, so you might find it interesting that there's a real connection to things in math that you might know. So here's a function of real variables, v, w, and z minus v plus w. And this is increasing in z. So if you raise z up, the value goes up. And it's decreasing in v and w. Another way to say it is that the partial derivatives are, positive and negative, and like that. So what this actually means, another way to say it is that if you have z1 less than z2 and v2 less than v1 and w2 less than w1, so notice that I have it backwards for the 2 and the 1 on the v and w, and forward for the 1 for the z, then you could conclude the left side here is less than the right side here. So that's another way to say the whole thing. And that's what somebody would mean if they put arrows on the variables v, w, and z like this. Now, if I had an absolute value here, like this absolute value of w, there's nothing I could say here. And I would want to make a parallel kind of statement. The best I could do would actually be insist that they're the same. So the only way I could get a true statement out is to put equals here. If Z1 is less than Z2 and V2 is less than V1, and the W's are the same on both sides, then, and kind of only then, could I conclude this inequality here. So that's what this equals means on these. Okay, so what we're basically trying to think about is a parallel between the English meanings of sentences in words and contexts, especially the influence of the determiners like every and no, and this algebra kind of example like these. So if I say every man and no woman sleeps, what I want to do is to kind of like replace these by variables. Every X and no Y does action Z. So every X and no Y. And there's an account of formal semantics, which gives you exactly a recipe for how the meaning works. And then and it would have the same feature if you assume that X1 is less than X2 as the kind of things that we could put here, namely nouns. And the same thing for the Ys. And if the Z's were absolutely the same, then you could conclude an implication, because an implication is just a monotonicity statement where the codomain is the Booleans true and false. So that's the connection of this kind of notation. Oops, what I have at the bottom with the one about algebra. So am I going too fast? Is this okay for people? Let's see if anybody wants to say anything. Does anybody want to ask about this? Okay, thanks. Okay, thanks to Corey and Damir. Okay, all right. But if anybody wants to ask, please do. So the way that von Bentham did it was he actually he used Montague's categorial grammar with so I'll explain exactly a little bit about, give you a taste about what that means, and then he put decorations of negative and positive where I'm putting like the arrows plus and minus. Now I actually am following a different approach to the whole thing that David Dowdy kind of put forward, which is that
Larry,
yeah.
I think there's a question in the audience.
Oh, super! Thank you. Let's see who wants to ask. Okay, yes, who would like to ask?
Yeah, this is Gilbert Plummer.
Hi.
Yeah, I'm still trying to figure out your table, natural language information table. At one point, I don't know if you can go back to that slide, but
I think I should. This table?
Yeah, why is every less than or equal to most?
Yeah, okay, so for logicians, of course, you wouldn't say that. But if a person says, you know, every student read a book, then it kind of follows that most students read a book. Now, for a logician, you'd say, well, what happens if there aren't any students? You know, what about the empty set? If you put that aside, okay, that's interesting. But if you set that aside, then actually every would imply most. If it's a non-empty set, then actually then every implies most.
Okay, I see what you're up to. Thanks.
Yeah, I'm really trying to do the human one, not exactly the logician's one. That's yeah. Okay, thanks. Okay, good. Yeah, feel free to ask questions about all this. Yeah, that's definitely right. Okay, so let me go on further. So I think I will try to do some of this quickly to show you how all of it works. Yeah, I'm going to try to give an overview of the math here, especially if you know about the syntax-semantics interface that categorial grammar provides us. And then I will try to show you how the whole thing works in practice. So I think I will try to do this, not forever, but for a little bit. Okay. So for those of you who have who work in semantics, because I know that UConn's group in linguistics and philosophy is has a whole extremely great presence in semantics. So the kind of thing that I'm doing on a mathematical level that I want to interest semanticists in is to move from sets to preorders in semantics. So this I feel is a kind of an important step that I think should be explored. So I want to replace sets by preorders in semantics to do this account of inference. And let me say let me sort of show you how all this works. So a preorder in math is a pair of a set together with a relation that's reflexive and transitive. So reflexive means everything is less than itself, and transitive means just what you would think. A is less than B, B is less than C, then A is less than C. So preorders are all over the place. It's one of the most common and vanilla kinds of structures in mathematics. So here's one example. The preorder of truth values is like this. The preorder of natural numbers looks like this. They don't have to look like lines, and you'll see in a minute. And upward is bigger. So usually I would think of false as below true, and 0 is less than 1 and less than 2, etc. So this is how they usually go. And for any kind of preorders, there's also an opposite preorder, which means you turn the preorder upside down. So P is less than Q in the opposite. So P op means the opposite preorder. If Q is less than P in P. So that's the opposite preorder. And not only that, there's also a flat version. So if you take a preorder and you flatten it, what that means is you declare the only kind of interesting inequalities in the flat version are the equalities. So P is less than or equal to Q in the flat version, if and only if they're absolutely equal. So that means you have made it the picture of it would be flat. There would be nothing above anything else. There's also a product preorder. So if you have seen products, you'll see this immediately. And if you've never seen it, it'll be too fast, but let me look, here's some pictures. So here's 2 from before. This is the true false preorder. This is 2 op. So I put true below it, and this is 2 flat. It goes like that. Here's the natural numbers. Here's the natural numbers upside down. 0 is at the top. And here's the natural numbers flat. They're all sort of laying out on the table, the flat table. Now, if you could multiply things, so here's 2 times 2, you compare them pointwise. So flat false false is less than true false because they're less than each other spot by spot. So this is 2 by 2, 2 times 2, and this is 2 times 2 upside down. So I took the 2 times 2 over here and flipped it upside down. This is 2 op times 2. So I took the 2 op times 2 and notice it's different than all the others, like that. And this is 2 times 2 op, which is this one upside down. And so I'm doing this. So now I want to talk about monotonicity. So a monotone function between preorders is one where bigger inputs give you bigger outputs. Or more literally, if one input is less than or equal to a second one, then the outputs respect that. And so this is a very, so the reason for doing all this stuff in preorders, it's the mathematical setting to talk about monotonicity. And I'll write this as f goes from p to q with a plus over it, which means I remember that it's a monotone function. Antitone means we flip things. So if p is less than q, then f of q is less than or equal to f of p. So that's an antitone function. And I'm going to write that as f goes from p to q with a minus on the top of it, like that. All the stuff having to do with inference and negative words, or even words like every. Every was down in its first argument and up in its second. It has to do with monotone and antitone functions. So here's negation. So negation looks like this. Here's 2, and here's, oops, this should say 2 op down here. I think I have to fix this slide. I think I'll write these down. So this is negation on the Booleans. It's definitely an antitone function. But you could straighten it out by, let's say, if you took it from 2 op to 2, that would be fine. Oh, somebody else wants to ask. That's cool. Okay, thanks. Okay, and so I would write it as negation is a function from 2 to 2 that's actually antitone, but as a function from 2 op to 2, it's actually monotone. So if I go back over to here, now I've flipped the domain from 2 to 2 op, and now it's a monotone function because the ordering here is true less than false, and the ordering here is false less than true. Now here's the arrow. So the arrow, if you think about it as a function from 2 op times 2, one of the 4 that I showed you before, into the Booleans, this is standard material implication. Material implication is a monotone function from 2 op times 2 to 2. And what that means is that I could type it like this, that the arrow as a higher order, as a function, it's a function from here to here is monotone. Now I could even, this even has a message for us. So that means that the arrow, just like every, is actually antitone in its first argument and monotone in its second. So if you have an if statement, it's down in the antecedent and up in the consequent, which, so if you have a theorem, the theorem gets better if you make the hypothesis weaker, if you make the antecedent weaker, and it's better if you make the consequent stronger. So this better means that the point about better is this arrow here. And what this says is that if you make the antecedent of a conditional stronger, or the consequent, if you make the antecedent weaker or the consequent stronger, you get a stronger conditional. And all that comes out of this picture here. That's what it is. Now you can actually take this arrow thing like this and curry it. So if you have seen currying, which is the way to take products into higher order arrows, then you'd get this kind of a summary of monotonicity. So this is the way things usually go in the theory of grammar, where we prefer to have higher order functions to functions on product spaces. So let me see how we're doing here. Okay, for any preorder and any set, we get a set of functions, a function preorder. So namely, we take all the functions from the given set to the preorder, and we order them pointwise. And it's easy to check that we get a preorder this way. So this is how we get, so we need this because everything in semantics is a higher order function. So we definitely need this kind of thing. So we saw monotone and antitone. And in order to handle things like that most, I'm going to want to have another kind of notation, which is this dot, which means a regular old function. So f from p to q with dot means there's nothing I can really say about it. If I put the minus, it means it's antitone, and I put the plus, it's monotone. And the important point that I'm going to use is that every function from a flat preorder is automatically monotone, and automatically antitone also. If the domain is flat, then it has all the properties that you could ever want. Now, when we do semantics, we frequently say, let's say the meaning of type x to y is the set of all functions from x to y. That's how Montague grammar and formal semantics typically works. But when we do the pre-order version of everything, this idea splits into three pieces. So given everything now, it has to be a pre-order. And so if we're given P and Q as pre-orders, we can form the pre-order of all monotone functions, right? The pre-order of all monotone functions is the suborder of the function space order. And we could do the same thing for the antitone functions and the same thing for the all functions. And in all cases, we get the pointwise order. Just the point that I'm making is that we now split this idea of function space into three flavors. And the reason that I want to do this is because I would like to do things in semantics like, at most one is less than at most two. Like if I, or at least two is less than at least one. This will be easier to understand. So if I tell you at least two people are falling asleep during my talk, it follows that at least one person is falling asleep. If I say at most one person is falling asleep, actually it follows that at most two is. Stuff like that. So, and I want this, and the space that this is working on is the determiner space, which in terms of semantics is a fairly high leveled space. So when you do categorial grammar, you have arrows like this. So if you have never seen this, you won't catch it now, but you will catch the flavor of it. You have arrows that go like this in the syntax, and in the pre-order version, I want to put in three kinds of flavors of monotonicity information. And I usually would start, so the way that we start in semantics is usually semantics start with E for entities and T for truth values, following Montague. And so I usually would insist that the pre-order for the entities is a flat pre-order, right? If I think about the people in the room, it's unordered in any kind of interesting way. The truth values is always ordered. And I'm going to want to use numbers, so that will be ordered as, let's say, the natural numbers. Okay, good. So now this is the phrase. So E to T is the type for things like intransitive verbs or nouns, and ETT is the type for noun phrases like the man, stuff like that. 5 birds, something like that. Now this is standard in semantics. You spend a lot of time with ETT. Now ETT breaks into 9 pieces here because you have 3 choices for this plus and three choices for the first arrow and 3 choices for the second. And now the question is, is this useful, or is it kind of just a big extra, for nothing? So I mentioned before that every function from a flat ordering is always monotone. So that means that these 9 here basically collapse. And the only ones that we have really left are these ones. So E to T so these are all the same. E to T, E, since E is, I interpreted flatly, this one flatly, and this one dot, they're all the same. And I'm going to call this property. And so what we left with is actually only 3 versions of the noun phrase type. Property to truth value, plus, minus, and the dot. And so now this is the way that a usual linguistic account would go. I associate with a bunch of my words, syntactic categories. So like these are names, so let me make them noun phrases. Cat and dog are nouns. Swim and run are intransitive verbs. I'll show you how this works in a kind of impressionistic thing later. Here's the quantifiers: every, some, no, and most. These combine with a noun to the right to make a noun phrase. This is the relative clause, the relative pronoun who and that. It looks like this. There's something about negation. This is the Boolean and. This is if then, looking like this. Here's numbers, and here's like more than and less than, like more than two. More than would combine with a number to its right to form a determiner. And now I'm going to make the semantic types. So this is also very straightforward, except that I'm putting in the inferential information afforded to us by the blue plus, minus, and the dot into the semantic types. And the reason that I do that is that I can later on put in things like, this is a picture of some dog chased no cat. So it would come to us with this, like in the syntax, without all this arrows and the plus and the minus. And our computer program fills in all the rest of this. So let me show you a little bit of how this goes. It actually has to do a lot with composition and other kinds of mathish work. So it's easy to check that the composition of monotone functions is monotone, and the composition of a monotone and an antitone is antitone, and the rest of this. And when you do this, you very quickly would like to make a chart, like a multiplication table of how this works. And everybody, the math guys, will see that this is just an isomorphic copy of like multiplying negatives and positives. So it's just basically that. So here's the kind of way, if F goes from P to Q with a marking M, and the marking could be either plus, minus, or the dot, and N goes from Q to R with the marking being dot, then we kind of compose them, and the result has to marking MN, which is given by this chart at the bottom. And now if we want to do more, if we want to talk about, how does this work with function application? So what I showed you before was function composition. So function application, you put down a whole lot of this kind of things here, and then everybody would cringe by saying, isn't there a formula for all this? And so the formula would be fairly similar. It would involve taking a marking in blue and a polarity like this, and making this chart. And this would tell you how the M here and the polarity arrow on the P, whether it's going up or down, kind of behaves with respect to function application. So if F is a monotone function from P to Q, and this says we can kind of raise the P up or lower it down, whatever, and it would follow all of the laws that are given by this pattern. And so then we kind of take our categorial grammar rules, which are basically the first three up here, and we come up with ordered versions. So we do the math and we figure out how inference has to work. And in fact, you get three more of these that have to do. This is a very sophisticated one that I guess I would only talk about if somebody wants to know about it. And these are kind of forms of weakening, like in math generally. So then basically what would happen is, let me say, you would read in a sentence like, every cat that Fido chased ran. And the top box here is what the parser provides us. So the top box actually says, I'm giving you a parse. How does it get a parse? The parse is somebody else's problem. The system gives us a parse, and it's like this. And I would like to figure out which way the arrows go. And I basically say, all you have to do is match my 6 rules. So you can match it with any choices of M and D. And so it's in fact a kind of a constraint satisfaction or unification or matching problem. And you find out that this is how it has to be. So it has to be that every is going up, cat is going down, that is going down, the Fido is going down, chase is going down, and ran is going up. So that means I have a way to do this on the computer, to go from the top parse to the bottom parse annotated with these arrows. Okay, and so you now can type in this stuff and do this like that. It will give you your arrows. You can teach this to people. You can run this if you want to download it. You can run all this. And here's how this stuff is used. So we would input a bunch of premises in natural language, and we would run it to the parser. We're with good faith in the parser. The parser is often right. Sometimes we don't like it. I can talk about that later. We work with the parses. Then we appeal to what I showed you today, which was a tool that polarizes it. That means it adds the up-down arrow. Then we use an inference engine, which is basically, in the best case, simply replacing according to the arrows. So that's monotonicity arrows. For those of you who know about like conservativity rules for the determiners, definitely comes up. Other rules of natural logic also come up. And we have a knowledge base like dogs or animals, you know, that we're not like going to get this from thin air. We're going to get it because somebody else gave it to us. So we have a knowledge base that we have taxonomic kinds of information that sometimes it's wrong, but we rely on it. And then we use this to give an automatic assessment of whether one thing follows from another. So this is my proposal on how to do logic for inference on sentences. It has a lot to do with, I mean, categorial grammar is very good because it has a syntax-semantics interface. I worked out the math of how this piece goes. Monotonicity rules give a good replacement, and we have enough of the other stuff sitting around that we could use. So that's what we're doing on this. So how good does it do? Well, this is machine learning, the best, which is 86% accurate. Our system, well, it's almost the 80-20 rule. Our system can get about 80. So MonaLog is the name of our system. So it's monotonicity and logic. It can get 81. It can't do as well as this. These are other logic systems that I don't think I have time to tell you about, but we're not the only ones playing this game of trying to do logic and inference on the computer. These ones are all, they have something really going for them. And in fact, on this pattern, they're actually better than ours, 97% really. And this in the inside here was the best machine learner at the time that we wrote it, and these keep getting better and better. So what could we do? We could go beyond CCG. So if there's anybody who works on this natural language inference here, I have a lot more to say, but I sort of doubt that anybody is. So let me go on. What I wanted to show you in 10 minutes was actually the part of it having to do with natural logic rules. So this is yet another way that I'm thinking about inference in logic, is to redo the entire way we think about logical systems and their relation to natural language. So here's a batch of logical systems. So this is a different part of the whole talk, and I will try to do this quickly. At the top is first order logic. As you know, first order logic is famously undecidable. So I have a line here. This is the church Turing line. So this is the undecidable ones, and everything below is decidable. I named the line Aristotle for logical systems that are syllogistic. The system that Aristotle did was pretty much this one called S for syllogisms. There are logical systems that go beyond what Aristotle would have done in the style that he did it, because typically they use variables. So the systems that are inside between these lines are decidable, but they use variables. The line for piano and frege is a kind of first order logic line. So the stuff to the right are things that are expressible in first order logic. This one over here and a bunch of other ones that maybe I'll point to are ones that couldn't be done in first order logic, right? They're not expressible in first order logic, but they're syllogistic and they're decidable. In fact, they're usually like in polynomial time and stuff like that. So the way I would like to think about this is like the way a linguist thinks about fragments. So in fragments for syntax or even semantics, a fragment is a small piece of language. So I'm trying to do fragment of language for the inference task. So I wanted to show you a few of these, like lickety split. So the A is the lowest of the chart. So it's A like for all, but it could also be for Aristotle. A, we start with a bunch of nouns, like animal names, taxonomic information. And the only sentences I have are all P or Q. So that's it. That's the only syntax that we have. And it has a formal semantics, namely the model is just a set together with an interpretation of the nouns as subsets. And I'll say that the model satisfies all P or Q. So this is for the 6 logic students. You know what this means. Satisfies, which should mean that the meaning of P is a subset of the meaning of Q. Okay, great. So there's some examples. Nobody needs to know this. And this is model theoretic semantics. So I'll say that one sentence is a semantic consequence of a bunch of assumptions should mean that every model of the assumptions is a model of the conclusion. So this is the usual account of semantic consequence that we do in model theory. And so now we have a proof system that matches it. That's exactly probably the simplest proof system in the whole world. So we have one rule, all P or P, that you get from nothing. And we get the syllogism Barbara as a rule, all P or N, all N or Q, it follows that all P or Q. So then we use this to generate proof trees. So here's an example. Here's a set of assumptions. And here's a conclusion, phi. And here's a proof tree. So what a proof tree means is that at every node, you're either a leaf, which has to come from our assumptions, or you're an application of Barbara. Or you could be all A or A. You could be an application of the axiom one too. And so this is a proof tree. And then you prove that this is complete. And actually, this is the simplest completeness theorem in logic. So I would like to think that Aristotle, who asked about completeness, didn't have the idea of syntax and semantics, so he couldn't have actually done this. But I would like to think that Aristotle would have done this. And the completeness of this thing is actually one slide. I mean, you can really explain it to people standing on one foot. And I think I won't do it for you, although I usually I would. The completeness theorem is completely simple, and you can give it as a homework exercise for the logic students. So if something is a semantic consequence, it had to be provable. That's completeness. And now, so that's the lowest logic in this batch. And so what are the other logics? Well, the syllogistic logic adds things about all, some, and no. So that's what Aristotle was into. All X or Y, some X or Y, no X or Y. The R adds verbs. It adds transitive verbs and relative clauses. The star actually adds relative clauses and iterated. So if I say, I'll show you a picture that this is more relative clauses and more stuff going on. If you add comparative adjectives, you get even more kinds of stuff like this. If you have a lot of negation, it gives you these ones with a dagger. So the dagger means I'm adding negation on nouns in a big way. So a lot of the interest in these logical systems comes from negation and how it works and doesn't work, and it makes all the interest in these systems. Once you take one of these ones below here and add negation, sometimes it's provably beyond this Aristotle line. It means it could never be worked with in a syllogistic way completely. Let me show you a picture. Let me show you one other thing about this. So a logic that has to do with the word most. Yeah. Supposing I tell you these are the rules of all and some from the syllogistic logic. All X are X, all X are Y, all Y are Z, all X are Z. Here's the some X or Y. It follows that some Y are X. That's called conversion. If some X or Y, it follows that some X exist. And if some X are Y and all Y are Z, it follows that some X are Z, and this is the syllogism Dari. So supposing I add most here. So let's see, this is the audience participation part of the talk. So why don't you put down what you think the rules of logic should be if I add most to the syllogistic logic of all and some? So can anybody think of any rules of logic? Nobody's writing anything. So you should put it in the chat here if you have a rule of logic. There are 5 or 6. Well, how about I tell you most X are Y and most Y are Z? Does it follow that most X are Z? No. No, it won't follow. If I tell you, if I say most X are Y and most Y are Z, it shouldn't follow that most X are Z. Think about it. So you would get a contradiction, a counter example pretty easily. Nobody has any rules of logic. I hope I haven't gone too fast for you to try this out. Does anybody find any valid laws of logic? There's a few interesting ones. Yeah, what do I mean by a law of logic? I mean, good, thanks. I mean something like this syllogistic thing is like it should have a premise, like one or two premises and a conclusion, and it should always be sound. It should always be, you should be able to depend on it. So how about if I say, most X or Y, then some X or Y. Okay, good. That sounds great. So thank you for Corey for this one. Yeah. So most X or Y, you can conclude some X or Y. Any others? There's a bunch of other interesting ones. Okay, so let me show you the laws of logic here. So this is what I give for I'm teaching an undergraduate class, and I often give them a fragment of logic and tell them, for homework, you find the laws of logic or you prove the completeness. Okay, so I think this was the one you put. If most X or Y, then some X or Y. So this is M1. Okay. If there are X's, like if some X exists, then most X are X. So you can count on that. If most X are Y and all Y are Z, then most X are Z. That's great. Now, if the X's and the Y's are the same, this M4, if all X are Y and all Y are X, then they're actually the same set. And if you know that most X are Z, it follows that most Y are Z. Now, as you go farther and farther in my chart, you get ones that are harder and harder for a person to actually understand. Here's one. If all Y are Z and all X are Z and most Z are Y, then it follows that most X are Y. So let's see if I have a picture. I think I have I didn't put the picture of this. This is the most interesting one in a certain way. And this last one is actually an infinite batch of rules, which the simplest one is if I say most X are Y, most X are Z. What follows from this? Anybody? If I tell you most X are Y and most X are Z, what follows? Some Y or Z. So if the X's are more than half of the X's are Y's and more than half of the X's are Z's, it follows that they have to have some overlap. So this is the pigeonhole principle. And then you could ask, well, is this the complete thing? So in fact, it is the complete thing. So this is the simplest one. The next simplest one has like 10 premises, something like that. In fact, this is complete, and yet it is like a second order kind of thing, but by itself, it's actually completely tractable. It doesn't give you a headache to think about it. It's not problematic. It works out nicely. So I know that I'm about out of time. So let me mention a few. Let me wrap up this here. I wanted to thank a bunch of people. So my PhD student, Hai, is the one who did all the implementation of the up and down arrows. All the connection of this with machine learning comes from a group that gets together to do this. With Thomas Eichard, the Stanford Philosophy Department, I've kind of worked on this monotonicity with lambda calculus and some aspects of this categorial grammar kind of stuff. And the annotation, what I was showing you about in first, is part of several teams. So what I want to do here is to show that parts of natural language inference could be done in decidable logical systems that don't translate to first order logic. I'd like to see the axioms to get a complete axiomatization. I want to make connections to all of the fields of logic, like complexity theory and finite model theory, decidable parts of first order logic, algebraic logic, all that kind of stuff. It should have a nice interaction with all this and computer science logic topics too. After all this kind of work, I feel that this inference is a very problematic thing, so I could talk about that for a while. I feel like we should be trying to join the perspectives of cognitive science and linguistics, semantics, computer science, machine learning. We should try to do all that kind of stuff to actually have a good story about this inference. And I've learned a lot by making running systems. So I've actually learned a lot by doing the implementation and working with people doing it. So here's all the people that I work with. And the last thing is doing this natural logic allows us to live in two kinds of worlds. So this is what I love about logic, is that it's a very classical subject. I mean, this is Aristotle and Leibniz. It's maybe the most classical of the subjects going on today. At the same time, here is the computer that beats the human in Jeopardy. And so logic is not only a classical subject, it's like a hyper contemporary subject. And what I love about doing logic is that I get to do both of these. So that's what I have for you today.